So this one should be the one. All right, should be good.
That's it.
Okay. Yeah, thanks, Rob, for the presentation, introduction. So today I'll be talking about lowering barriers to chip design using OpenFAB, as well as the activities we do at the analog working group with Rob Maines here. So first of all, I'll go a little bit and give an introduction of who we are here. Our project started with FASOC, which is a DARPA program. It started 4 years ago or 5 years ago. It was a multi-university and industry effort. There was Virginia, Michigan, and ARM through the DARPA funding. So I gave a couple talks at CHIPS Alliance. There's a couple stuff that you can go and check there, basically the framework and how it works. I don't want to go too much into details. I'd like to focus on what we've done this year, the tape outs, and some of the updates on the methodology and on the flow. So these are a couple tape outs we have done over the course of the program. These are mainly using closed tools, but also open source tools. So we started with the TSMC65 LP design. We taped it out and demonstrated it at Salt Lake City, I think 3 years now or 2 years now. And then we did a couple of tape outs in GF12. We included more generators. We actually do analog generators if you didn't understand, but we included more blocks and more circuits there. And we demonstrated that, published it in a couple of conferences. And then when the initiative with Skywater and Google started, we started with much more tape outs. So those are a couple screenshots of our tape outs, and I'll go into more details as we go. So now after the program from DARPA ended, we don't have the funding. So Google was one of our benefactors, and NIST as well. We went to the umbrella of CHIPS Alliance and the Linux Foundation. We collaborate a lot with the OpenRoad, and we started using tools like GDS Factory and Align. And there's a couple updates on internet, on YouTube, on these talks here through CHIPS Alliance, so please go there. But my group is a small group. We have 5 students and a postdoc, and we're working on a couple generators still and a couple tape outs. So how does it work? I'll just go briefly, just to remind people here what is OpenFAB. So OpenFAB addresses automated analog design, right? And here I made a really small workflow diagram on the left of what would be a traditional analog layout flow today. And as you all know, most of it is custom and require multiple iterations from schematic entry to layout, then simulation, and so forth. While the digital flow or the grid-based flow is highly automated for a while now. So the idea is basically to take what would otherwise be a full custom analog layout and shoehorn it into it. The cell-based digital automated design flow methodology, which is pretty amenable here to the available logic synthesis and place and route tools, either be it proprietary or open source tools. So this is the whole framework. This is a couple of legacy design from ISSCC, VLSI, and CICC. There's much more of these blocks here. I couldn't fit them all, but there's much more that we have created, especially on the open source side. These are the auxiliary cells. So basically, we try to identify analog functions in these blocks or circuit, which are highlighted in blue. And we try to split them in small blocks or auxiliary cells so that we can create standard cell and shoehorn them in the digital flow. So you can have a lot of variants of these auxiliary cells. They are usually 12 transistors below, and they are very easy to modify to create multiple variants of your design. We also added some support of Align tool. It's a little hard when you use a vague layout generator these days, but basically we try to add some constraint to Align to create our auxiliary cells. So that makes it the last piece of automation of OpenFAB. So here, so this is the the tool chain we've been using in the DARPA program. It's called FASOC. It's based on proprietary tools. It's using Synopsys, Cadence, and all the closed tools. But my focus here is about OpenFASOC, and we 2 years ago we started the flow based on the existing open source tools, Yosys. We started using sometimes Sherlock and UHDM thanks to AntMicro and Google, OpenRoad, Magic, NetGen, KLayout, and GSpice and Xi. So that's the whole tool chain we are using. But you can see it on my last update in the Chips Alliance Tech update. We started using much more stuff in there. We started using much more customized layout, and we started using something called GDS Factory, which is supported here in Google by Joaquin, who is a photonics guy. So we thought that tool, through a tape out we've done with NIST, was very, it was perfect actually for what we wanted to do for test structures. So we started making these Python APIs that basically create polygons that, create for you test structures that are useful for your design. So I'll go in more details, but that basically evolved our flow into more than basically just using a cell-based approach, but using also a customized layout, which is really required for some of the analog blocks if you're used to analog design. So anyway, so I'll move now to the tape outs. These are all tape outs. These are 2 years ago, MPW1. We made a sensor array. We made 64 of them using the Skywater technology. We included an LDO that we've never been able to test, but the Temp Sensor are working, and we published the work in the solid-state circuit community, or solid-state circuit letters, which is pretty good because it's state-of-the-art and shows really good results. So I'll go into more details here. To make that Temp Sensor, we had to create some functions or functionalities in OpenRoad, like voltage domains that you can see on the right, and non-default routing. So these are very useful in analog design, but they can be also very useful to anyone who's doing custom design. So actually, in our repo, I mean, there's 100 star, but there's a lot of people that are using our scripts to do their custom layouts, which is really good. So these are the measured results. These are not simulations. We were among the first to have Seacon working in this technology. This is the good thing about generating 64 sensors is that you can map the design space exploration. For Temp Sensor, there's a couple metrics that are interesting here. There's inaccuracy, resolution, time conversion, power. So here you can just decide which sensor you want. And this map is probably changed over this past 2 years because we've been updating our tools and flow. We also used multiple flavors in this technology. So there's an HD transistor, high density standard cell library, and the high speed one. So it gives you different footprints in your chip. And that can be useful depending on what inaccuracy or how much area you have, right? These are more results. We actually tested the 64 sensors, so we made some Python scripts, and they are all on GitHub. The chips are available if anyone wants to test them, but we generated all this data here, measured data, and we have a below 1 degree C inaccuracy, which is state-of-the-art. And you can go in, the data is available on GitHub. You can go and dig in and see what is interesting to you. This is a comparison table. We do research, so we have to compare to other people. We compare to JSSCC, CRCC, and ISSCC papers, which is really great. One thing that I'll highlight here is the conversion time is really, I mean, it's decent compared to others, but it's horrible for our previous sensor. So we improved that, but one of the sensors is really good. So anyway, having been able to generate multiple of these sensors allows you to get different trade-offs, and that can be very important to a designer, especially if you're doing an SoC or any system. All right, so this is another tape out. You still didn't get the silicon back. Hopefully we'll get it soon from eFabless, but this is MPW2. We did the same thing, but now with a digital LDO, we did 10 of them. We simulated them and everything, made sure everything's fine. We created some debugging because you can't just put an LDO and hope that it's going to work, right? So we had to do some analog buffers, voltage references. We also included an OpenTitan SoC there as a demonstrator, and we included 4 of the best temp sensor we have. and we thought we were good. We also developed a flow for ECO that basically fixes hold violations. So we're hoping this chip is going to work. Yeah, we updated our digital LDO. We embedded voltage references, decap generator, and voltage reference circuits. I think that's what I wanted to say there. This is just a zoom in into the LDO. As you can see, we try to constrain our design. If you're not familiar how we do that, you can listen to our or go check our other talks. But basically, we try to use Python-based constraint or since this is open source tools, we create some functionalities that allow us to do a better layout, right? So basically, here you can see that the arrays, the power switch array here on the bottom is actually structured in a manner that allows you to have less variation, right? And then we make sure the power mesh is actually built in a way resistivity is really low and there's no narrow routing or single via cuts. We also included a highly trimmable voltage reference. It's based on a 2T voltage reference we do in Michigan. It's actually a little more than that, but it's over here. But basically, that allows us to calibrate for variation or basically models not being good. There's different issues that we are trying to anticipate here. Yeah, so this is another. There's a couple things here. This is the top diagram. We are using multiple switches, so there's 10 LDOs. You're asking why do you need 10 LDOs? Well, we wanted to address different loads, first of all, but we also wanted to try different circuit techniques, right? So we used, the SkyWater has a native transistor, so that's great. We used that. We used the PMOS as well, different sizes. We used a standard cell-based comparator, but we used a stronger arm latch comparator as well. So I think that's very useful because you can generate thousands or hundred thousands of these LDOs. We just generated 10. But you could do that and simulate them without taping them out and see which one is great. So I think that's very useful. All right, so this is the top diagram. I think we were the first one who made an AMS or analog mixed signal SoC. Hopefully it's going to work. I'm not going to go into details into the ECO flow, but we can discuss it if you want to hear more about it. But the idea of this ECO flow is actually to improve the power. Initially, we used it for to fix hold violation, but that's not the only goal. We are targeting energy efficiency, and we want to reduce leakage and a couple other things. So this ECO flow is very useful for this type of things. Right. So the other tape outs we made are for the NIST nanofabrication accelerator, and that's an initiative under the umbrella of Google and NIST. We work with a couple other faculties from Brown and GWU, which is really great. We have a weekly meeting. If anyone is interested, I can invite him to that meeting. But the idea there was to make test structures for cryogenic modeling. If you're familiar with that here, basically you have to interface with the quantum processor, and interfacing with it at 200K is not great, right? So you want to be able to run your circuit at lower temperature, which is 1 to 4 kelvins. So, and before doing that, you have to generate building blocks for that. So OpenFAB sounds like a good way to do that. But first of all, we need to create test structures to do this thing. So we worked with NIST on this part with Brian Hoskin, who is the PM of this program. And we taped out this chip here around first quarter of 2022 with one of my students. And I'll try to go into, I'll just review some of the test structures here. There's MOSFET arrays. These are very simple structures: line resistance, via resistance, precision resistance. So these are really simple structures, but I wanted to automate them, right? And OpenFAB is a cell-based approach. So how do you do that? So that's where GDS Factory popped in. And we started using Python-based APIs to create these layouts here. And then that's where we discovered this could be very useful to our other generators, like a PMU, which has a lot of fly-in caps, switches, power switches. That's very useful for ADCs as well, DACs. So I think this is awesome because you can also integrate some of these customized blocks with a cell-based approach, and then you have a diminishing return rule here where you can, you don't spend a lot of time on the part that doesn't require attention, but then you spend some time on writing some Python scripts for some of the blocks that require attention, like a DCO for a PLL, flying caps, So anyway, the other blocks we made is this ring oscillator here. It's an interleaved placement, as you can see on the left. This is very useful for process centering. This is using Python based manipulation of the dev. So we're hoping in OpenRoad we can have a better interface to it. There's a couple of people working on VLSI IR or other tools that could potentially do this work here, where you don't have to deal with different formats like def, GDS. Right? So, but anyway, this was one of the blocks we did with the OpenRoad. The other blocks, we made 24 sensors of them. This is using OpenFAB SOX Flow cell-based approach. We also included the OSU standard cell libraries from James Science Group at OSU. This is a couple other layouts. But the idea there, if you can see, there's a couple mesh there. And I'll just zoom in here. This is an example of a routine or API we created in GDS Factory, where it takes in dimensions, pitch, layers, and it creates a mesh for you. This is very useful. There's a lot of functions being reused here to create the mesh. There's not only the memcap mesh, there's diodes, there's momcap mesh, there's moscap mesh. So there's a lot of them, and you can reuse that for using this same function. And then we integrated everything using bare dies. These are bare dies that are probed, so they are very useful, sorry. But basically, the idea here is that we were able to reuse this function here in our other generators, and that's how we added more customization in our automated analog design. This is the resultant test die. It was really impressive because this was done in 2 months. This would require a year or maybe 6 months in a company. So this is really awesome to show. But the other interesting thing is we didn't only do MPW5 this year. We did MPW5, 6, and 7. And this is every 3 months. So, and we are actually loading, well, basically working on MPW8, where we are using actually much more complex structures. So you can see these are very, very simple structures. As you can see here, we included the PMU, ReRAM structures that was done by GWU. It's on the right there. But the PMU is where we use those routines for mesh arrays, flying caps arrays and power switches arrays. And the last one had inductors, as you can see there, VCOs and TIAs. So it's getting a lot more complex, and we still can tape out in 3 months. I think that's by itself a data point where you can see that this framework is working, right? In MPW8, we're working on a quantum current standard, which is a very complex circuit. And this quantum current standard is trying to detect single defects in a transistor. So we have to generate stats. So the idea here is we are trying to generate as many as possible with different transistor sizes and different blocks in it. So I think it's very, that could be a very high impact project if we can get it to work. Right. So this was about the NIST project. Meanwhile, we did another tape out in MPW0 for GF180, and that was done in less than a month. What we have done there is very simple structures where we wanted to discover this PDK. We have never used it, but one of them is a filter, GMC filter. It's all synthesized. They synthesized ring oscillators. So we used the ring oscillators we did in SkyWater 130, which is just the same code. So that's why we were able to do it in less than a month, right? So there's a lot of use here. We also made an array for non-volatile memory. So we're trying to see how it's going to work. That's just test structures here, but I think it's going to be useful for the next tape out. So if you want to build a non-volatile memory. All right. So the other exciting projects we did are in FinFET, and we are using open source tools here. So some people don't believe that, but that's possible. And we have done it in GF12. A while back, so we taped out an OpenTitan SoC, same as the one we did in SkyWater 130, but including sensors and using OpenRoad as the main open source tool. So there's nothing else other than OpenRoad here. Synthesis are using commercial tools and verification. So we were able to tape out at 250 megahertz, which is really great. Simulation is working fine. We have the chips. We are still debugging and see what is happening with them. But we know the functional verification is working, and also but we'll see what's happening with this chip. The other tape out we did recently last November while doing the other tape outs is the Intel 16 one. It's another OpenTitan SoC version which we built from scratch this time because we want to make sure everything is right. So we made this OpenTitan SoC, a crossbar, an array of temp sensor which are actually using an end-to-end open source flow except the PEX extraction, which is one of the missing points here. This is a couple diagrams or screenshots here. The green stuff is the buffers. So these tape outs help us push a little bit the limit, right? And the limit here, as a group who works on low power design, is achieve energy efficiency. So these are resizer inserted buffers, and we're trying to see why there's so many, right? Like we're not doing near threshold operation. So these are a couple of things that through this tape out, we can discover a lot of issues that can push the limit forward for open source tools. And we were able to tape out in 64 with a 64% utilization, but we had to roll back to 29 because in OpenFAB there is no support of multi-height cells for the tap cells, which is a very specific things in this Intel technology, and we weren't aware of it. So we could have anticipated that a little more, but we still were able to do this and actually make sure everything is working here in this tape out. So we're running at 28 megahertz, which is much more slower than the GF12 one, but that's because we just want to make sure everything is working using our framework here. These are power number. This rolls back to my point there about ECO flow. If you see the worst case corner here, we have a high leakage. We want to operate at, we want to achieve energy efficiency, right? And, we're trying to discover or trying to figure out how we can improve that by, the way we insert buffers. So leakage there means that there's a lot of buffers sitting around and just like consuming leakage, right? So these are issues that we could, this is, the tape out was done like 2 weeks ago, so this is still fresh. We're still doing a post-mortem. We start trying to figure out what are the issues and everything. The other cool thing here is the temp sensor. So we made another variant of the temp sensor. The temp sensor is based on native transistors. It's leakage based. It's running at sub-threshold. FinFET technology doesn't have a native transistor, so we have to figure out how to make it. So anyway, first thing, we used open source tools from RTL to GDS, and we were able to generate this array of sensors. Each of them is different. I'll go in details here. So there's a first variant A, which is using a VGS equal to 0 here, which is equivalent to having a native transistor. If you can check the numbers, we have a 0.13 inaccuracy, which is really awesome. This is PEX results using commercial tools, of course, but we are confident this is working. The energy per cycle is below nanojoules per conversion. 0 is 0.1 millisecond. So this is really awesome, and those are the corners. Or worst case corners we have. So it's still really decent results. This was done, this is a 2-month tape out with 2 students. Okay, the other variant is the virtual VDD inside the temp sensor has a very low voltage, and that can be prone to variability. So we're trying to get that VVDD to a higher voltage and make sure it is going to be functioning. So that doesn't require a lot of work from me, basically only changing this cell here, which is 2 transistors. That's very easy to do, and you can generate multiple variants. You can see the inaccuracy is bad, but the reason is, it's not bad, it's just below 1 degree C, but it's worse than the other one. But the reason is I want to make sure it's working. The other structure here is actually a diode with an NMOS, and basically this for the same idea, we want to see how it's going to work in the corners. And you can see that the typical is 0.35 degrees C inaccuracy, but it's getting better at RSS, right? And on silicon, it's probably going to behave differently. So that gives you a good idea of the silicon and how it operates. All right, so I'm done now with the tape out part. I'll talk a little bit about what we are doing in CHIPS Alliance and our working group. There's a technology design loop we're trying to define here with Rob, and there's multiple other people from the community that are very excited actually to talk about these things. So that was a really cool thing to see the past months here in our analog working group. But one thing, before jumping there, I want to give you an example of issues we can see, right? We can get silicon working, right? And we can design things, but NGSpice, when I simulated the temp sensor I showed you earlier in Skyward 130, NGSpice was telling me, hey, you have a 3° C inaccuracy at -40 or -20. That, I didn't believe that. I knew there was something wrong. When I used the closed tools, there was 0.4. So that's basically eight times the difference. And that's just inaccuracy. That's a calculated number or figure of merit. There's different numbers. There's power, right? Like 500% difference. That's totally out, right, than what you are supposed to design. So that's very problematic for high precision analog design or RF, right? Like who's going to design, who's going to be able to shoot for design without having a good model? So our analog working group is actually trying to define a way of improving those models. And you know, Google has helped a lot through Tim Ansel and other people here, like in NIST and Coolcat, helped us to try and see what can be done. So what we ended up doing is we're working with the EPFL right now to test some of these structures. They already generated some preliminary measurement results. And they actually generated the preliminary model based on their SEKV extraction model. So these are measured results, and that's the model. But these are very high precision models that can be used, and this is just the initial work that we started to do here. So we're trying to define a roadmap here. There's a lot of opinions in modeling, how to do it and how to do measurements. We don't know. That's a science by itself, so it's very hard to do that. So we're trying to do to take decisions in a collegial way. Maybe it's going to take some time, but I think we can propose or to define a set of standard measurements that can then be performed on the target technologies, which are open source here. So basically Skyward 130, GF 180, and any other PDK we have. We can then use these measurements to check the models provided by the foundry and their PDKs using dedicated benchmarks. We can extract these models like SEKV or any other model to have the designers design analog and RF circuits in target technologies. And we can define or have standard measurements, and the modeling parameters, we can have them and release them on GitHub so everyone can check them and provide feedback. Of course, everything needs to be automated because we want this feedback loop here to be as automated as possible. So then when we move from one open source PDK to another, we don't have to do this work, right? And I think OpenFAB can help a lot here. All right, so talking about automation, a lot of automation is required here, right? And that means that we need a lot of continuous checks to make sure everything is fine. So OpenFAB generates a lot of designs. The tools are organic, they evolve. We want to make sure everything is working. We had the instances where OpenRoad made a push and it breaks our generator. So we try to make sure everything is working, still working, even though everything is evolving, right, in a positive way. So the idea there is to create the CI here that basically runs these thousands of IPs that you can generate and make sure they are not breaking or regressing. So one cool thing that Google is doing is the Google Summer of Code, and I got a couple of students through CHIPS Alliance, and they have been working with me over the summer, and we try to define these metrics here and design space exploration. So we were inspired a little bit by Andrew Kang on OpenRoad metrics. So we're trying to do the same thing here for analog design and define these metrics, which are actually even more complicated than digital design. So I think this is something I'm looking forward, and Sai is working with me on this, and he's very excellent at this stuff here. You know, the beauty of the curse actually of analog design is that the figures of merits of a single generator can be overwhelming, right? There's nothing. It differs from an ADC to a temp sensor to a DC-DC converter. So you have to create test benches for all of these, and we do that in our generators to make sure they are working. So we can reuse that as checks in a standardized manner and make sure any changes in our test case and our circuit in the tool chain doesn't break our design. So that this is basically a very simplified way to do it, but I think it's a really useful way for our OpenFAB SOC framework. We plan to use the same approach for the technology design loop and modeling, which require to improve models. So basically, we create the structures, but we want to make sure in a CI, when we do measurements, we compare different tools. We have XICE and ngSpice. We get different results from these tools. Which one is closer to silicon results, right? So these are very important questions, and we need to get an answer to that. And open source is, the open source community or initiative actually helps us define these things and move forward. The other thing we did is through CHIPS Alliance, but also with a lot of help from Google and key people in CHIPS Alliance, we were able to create this notebook competition called Coded Chip. So that was done with Professor Boris Merman. This is a new competition to the, and this is the first time, to the best of my knowledge, that we have something in the Solid State Circuit Society which encourages reuse, reproducibility of results, and open source chip design in software style. So we've run this this competition in the past 2 months. We had 20 submissions. Most of them were great. These are the results. These are the 3 first winners will be able at ISSCC, which is the flagship conference, to present their results, show us their notebook, and they'll get a travel grant thanks to Google and CHIPS Alliance. All right, so that was my talk. Thank you, guys, and please let me know if you have any questions.
Thank you, Mehdi, so much for an excellent chat. Any questions from either here in present, or we have one here in the audience?
Can you talk about your measurement capabilities to analyze so many actual silicon chips back so quickly? You're doing lots of MPW. What sort of labs do you have?
Sorry, I couldn't hear.
Can you talk about your measurement capabilities? You're making lots of chips, and then you're also analyzing them in the lab too. You must have substantial equipment or people or something to do that.
Yeah. So I mean, our group in Michigan do a lot of chips. We've never done as many. This is too many chips per year to test, right? So, but we did a lot. We're doing a lot of chips, and we test them continuously. Right, so we have the student to do that and the test equipment. One thing we want to try to encourage actually is reproducibility of results. And actually, we try to send our chips to different people. So NIST got interested by our DC-DC converter in GF12, so they are testing it. But I have a lot of Temp Sensor, and if anyone in the room wants to test it, just to make sure everything's working, please do that. But I've sent it to a lot of people. A lot of them try to test them, but it takes some effort to test the temp sensor, right? So it's from -20 to 120 degrees, so you have a temp chamber and all of that. But you can do small tests if you want. Yep.
Take one more question.
Your question.
Any more questions here in the audience or online? I just want to ask you two quick questions. One is, do you sleep? Mehdi always responds to my messages no matter what time of day I send him something.
Sometimes I do sleep.
Just curious, how long does it take you to port FASOC from one technology node to another?
Well,
and also, honestly, how much development do you have to do if you go to like a very modern node?
Yeah, so these generators that we spend a lot of time on them, and it takes us a month. Like the Intel 16 one, temp sensor was very smooth. But it wasn't like that the first time. We did in GF12 and Skywater 130. Each time it took us longer. But as we went, it became really easy. The BMU is it's much more complicated block because it requires GDS factory with open road integration. So that's not the problem is having the integration of these tools all together. That takes longer time. But building the generator itself, I don't think it takes a lot of time for us to do.
Thank you. Well, thank you again for your great talk. I really appreciate it.
Thanks, Rob.
Yeah, I'm afraid we are.
So our lunch reservations. Want to do one more and then have lunch and come back. We have room all day.
If we can do that, yeah.
Yeah.
Do you want me to ask? Why don't you go ahead? I'll let you.
Yeah, so we have the room for most of the day. We have a lunch reservation at